Hey there, young detectives. Today, we're diving into a mystery about training and performance. You'll discover how athletes train and why training more doesn't always mean performing better. But more importantly, you'll learn about a powerful tool called Generalized Additive Models. By the end of this story, you'll understand how GAMs can solve tricky problems, ones that simple models like linear regression just can't crack. Stick with me, and let's turn you into data detectives, ready to solve the toughest cases in machine learning. Let's look at this data first. What you're seeing on screen is a graph. On the x-axis, we have how many hours someone trained in a week. On the y-axis, we see how well they performed, maybe in a match or test. You might think, the more someone trains, the better they do. Well, not always. Notice the wave pattern? There are dips. Maybe on certain days, athletes get tired. We call that burnout. And notice how performance keeps going up too? That's because good training still helps overall. Let's bring in our first detective, linear regression. It tries to draw one straight line through all the points, just like a ruler held across the graph. Let me ask you this. The equation which most of us are familiar with is y equals beta, not plus beta 1 multiplied by x, that is the equation of a straight line. But y here is the predicted value or the actual value. I give you 5 seconds to think about it. It is a straight line, and y here is the predicted value. In order to get the equation for actual y, we need to add an extra term called error or noise. Here's the part even seasoned detectives miss. The errors must be normally distributed around 0. That means our guesses should be off, but not too much, and equally on both sides. You must be thinking, why am I telling about linear regression when the video is about generalized additive modeling? Stay with me for a little longer and everything will fall into place. It is clear, visually, that linear regression is just too simple for the data at hand, but as good detectives, we must check the facts and not rely solely on eyes. Linear regression works only when some very strict rules, assumptions, are followed, and one such rule is normality of errors. Let's now zoom into a smaller slice of the data. Say people who trained between 12 and 14 hours. Now, fitting linear regression to this data set gives us a straight line. Much better, right? Linear regression works if data is straight in a small window. Now, assumption, normality of errors says, if you pick one training hour and check many performances, the spread must look like a bell-shaped curve, normal distribution. And this assumption seems to be working in the current setup with exceptions of few outliers. The mean of the distribution of the many values of y for each x should be the predicted value of y. But if we check this for the entire dataset, most of the points will fall under the category of outliers. Note this important concept. Predicted value of y is nothing but the mean of the distribution of the errors for each value of x, and since there is an underlying assumption that x and y forms a straight line, this mean we are talking about is given by a straight line itself. Generalized linear models. Let's go one level deeper. Linear regression is actually a special case of something called a generalized linear model, or GLM. In GLM, we don't always predict the output y directly. Instead, we predict a transformed version of y using a link function. GLMs say, let's keep the linear model, but apply a transformation to y. These link functions can be anything depending upon the case. For example, in linear regression, we predict y directly without any transformation. And thus, linear regression is a special case of generalized linear modeling. But there are other transformations like logit link, probit link, log link, etc. Here's the table of some commonly used link functions. I'll leave this table for you to go through for a few seconds. Coming back to our case, let's fit the simplest link function called identity function, which gives us this nice parabolic shape. Can you spot if there is any discrepancy to what we have learnt so far? If the identity function works like linear regression, shouldn't we get a straight line here? Pause this video, think hard, or go back a minute in the video. Ideally, we should, but here comes another requirement of GLMs. Generalized linear models require a formula to work properly beforehand. They cannot assume the shape of the data. We can see that the data is parabolic in nature, and hence GLM is told to account for the squared values of x. In other words, g of y is still y, but now GLM is looking at the squared values of x. Now, looking at the work of identity function, we can see that the performance can go negative if we extend the x-axis. As per the data, negative values are not possible. Therefore, for our case, we will use log-link function. The shortcoming we are left in GLM is that they cannot assume the shape of the data, or in other words, are not flexible enough to fit different kinds of data, which in face is the requirement in many practical real-life scenarios. Generalized additive models. So far we have learnt that linear equation is y equals beta, naught plus beta 1 multiplied by x, and this works like the identity function for generalized linear models, which is putting a function on y. What if we put a function on x as well? You might be thinking that this is same as giving an equation to GLMs, which in fact is partially correct. But here, the function on x is not same for all the values of x. It has the ability to take shape of any data given using different splines. Let's bring out the showstopper of our lesson today, the most flexible detective, aka generalized additive model detective. You must define the distribution of the response, example, Gaussian, Poisson, gamma. The link function, example, identity, log, logit. This defines how the model connects the mean of y to the additive components. In our case, we will use log link function, and our target variable distribution is gamma. GAMs are able to provide flexibility because they look at different segments of the data. In order to understand the concept better, let's go step by step into the mind of this detective. GAMs start by dividing the data into different segments. These can be evenly spaced or data-driven, quantiles. If we divide the data into too many segments, the final fit could result in overfitting. Let's divide the data into just 8 segments to start here. In order to divide the data into 8 segments, we would need 7 vertical lines. Since we are dividing the data based on the range of x and not the percentiles, these values at x will be equidistant. The values of x where the data is divided is called internal knots. Now, the logical step is to fit each segment of the data with log-link function, assuming the target variable distribution to be gamma. But once we do that, it becomes evident that there was something wrong without assumption. Can you spot it? Look closely. The predicted values are not going below 0, and by now you must be able to spot the error we did. Since negative values are expected as per the data given, using log-link function is wrong here. Let's change these assumptions and use simple identity function with as assumption that target variable belong to a Gaussian or normal distribution. This means we are trying to predict mean value of y just like we learned in linear regression. I hope everything is clear so far. If not, please go through the video again before moving forward. It is crucial to understand these basics, but once done, I believe you will be able to use GAMs with full mastery. Now, the next challenge is area around the knots. As you can see, there would be sudden jumps or falls the moment predicted equation cross over the segment. Also, each of the fitted line is too localized to that particular segment, thus is prone to outliers or overfitting. We can overcome this challenge by including more than one segment while fitting the polynomial functions, but not all the segments at once. This should remove the effect of localization. And these different polynomials fitted at different segments of the data are called splines. Here is the example of such fitted splines with degree of 3, also known as cubic splines. Why cubic spline? Pause this video and come up with the best possible reason your beautiful mind can think of. Write in the comments if possible to help me understand if my teaching is creating any impact in your understanding. Let's see what happens if instead of a degree 3 polynomial we fit degree 1, degree 2, and degree 4 polynomial. Linear polynomials or degree 1 polynomials are too sharp at the joints. Quadratic splines are still better, but they create problems at the knots. Higher degree polynomials gets out of hands to manage and becomes computationally heavy. Cubic splines are like the best trade-off, allowing natural bending and smooth joints. Please understand, I am not saying it's not possible to use other degree polynomials, but cubic polynomials gives the best overall performance. Another points to see where most of the seasoned detectives gets confused is the number of segments each base spline covers. We have seen the problem with each base spline covering only one segment, But why 4 to be exact? Why not 2, 3, or 5 for that matter? This again is about finding just the right amount of the data. A cubic equation is a x cubed plus bx square plus cx plus d. It needs 4 pieces of the puzzle to get the correct shape. I am leaving to solve this nitty-gritty detail for later, but general rule of thumb is we would need 1 plus the degree of the polynomial of the basis function, or spline, which in this case is 4 segments of the data. Now that these basics are clear, what is left now is to find a way to get the final fit, and that needs to be the sum of these base splines. And while doing so, GAM takes care that the final line remain continuous around the knots as well. It matches the first derivative of the final curve around the knots to keep the slope same, as well as second derivative of the final function to keep the value same. Look closely at the 4th segment of the graph. We have 4 base splines. Let's name them. Now, the final function by GAM would be the sum of these 4 functions. Similarly, if we look at the 5th segment, we will get another function, something like this. In order for them to be continuous and joining at the same point on the knot, their first derivative and second derivatives are matched. Base splines outside there, segments goes to 0. So we can include, say, f1 of x in our second equation, but its value for the 5th segment will be 0. In nutshell, we have our final equation of the fitted GAM line as this, where bi of x is cubic basis spline, defined piecewise, and beta I is the learned weight for each spline. Even though each base spline only covers a small range, their combination builds the final curve. At any point, x4 splines are active, non-zero, and their values blend to create the actual value curve fx. Now that we understood what needs to be done and why exactly 4 segments are required in this example, how would the curve be formed, say, in the first segment? We can only find one base spline there? To understand this, let's name our 7 internal knots from x1 to x7. Also, let's get the minimum and maximum values present in our dataset as xmin and xmax. In order to get 4 required splines for, say, the first segment, GAM uses an interesting trick called padding. It adds 3 knots at the beginning and at the end itself, and tricks the base splines to fit, giving them the required 4 segments. In truth, there will be 3 empty segments for the first base spline, and 2 empty segments for the second base spline, and so on. Now that all the segments have the required number of base splines, it's time to understand how GAMs combine them and form a single function. It uses a concept called likelihood. The likelihood tells us, how likely is it that these predictions came from the same distribution as the actual data? If we assume a Gaussian distribution, this becomes, which is just mean squared errors. This likelihood function becomes more complex with the change in the distribution of the target variable. We do not need to dive deep into those mathematical equations today in order to understand the concept here. Each base spline can bend the curve. If we let them bend too much, the model overfits. So, GAMs add a penalty for too much wiggliness, which means penalize the second derivative of the curve, make the curve smoother. Think, what if we chose a second-order polynomial for the spline functions? This penalizing term will not work because a second-order derivative of a quadratic equation is nothing but a constant value. This is our final combined loss function, or in general, form for any distribution. When GAMs take into account the loss function, the strength of the penalty or regularization, as well as the first and second-order derivatives at the knots, we get a smooth, final fitted curve like this. And what about the splines? They are here. Look closely if you haven't been paying attention. Now the curve is smooth, but is it well fitted? In order to make it more wiggly, we just need to increase the number of splines, which in turn is giving less data to each spline to increase its smoothness. In nutshell, a GAM predicts the target variable by using a sum of smooth functions of the features. Where g is the link function, beta naught is the intercept. F is a smooth function for feature x built using splines, and p is the number of features. And each smooth function f is made up of a sum of weighted basis splines. Now, some libraries may vary a bit in terms of splines used in order to optimize the time and computational power, but the basic concept remains the same. Unlike a straight-line cop like linear regression, GAM lets every feature follow its own path, curved, twisted, or flat. But even this smooth operator has its pros and cons. Let's try to predict now for, say, x equals 17. Our link function is an identity function, so g of y equals y. Also, we have only one feature, so our final equation becomes y equals beta, not plus f(1)17. Now, we have used 40 splines to get this nice perfect fit, but for any value of x, on our case, 17, only 4 base splines will be non-zero. Weights of rest of the splines becomes 0. So, our final equation becomes y predicted equals beta, not that is intercept plus f(1)x. And this function itself is the sum of the 4 splines. You can visually see the predicted values by each of these 4 splines in the graph. Now, I am leaving doing all the mathematics to calculate the final value, but concept should now be much clearer to you. And that's a wrap on today's investigation with our smooth detective, the generalized additive model. I hope this case helped you understand how GAM connects the dots, one feature at a time, with curves that tell the truth. Thank you so much for spending your time with me. I truly hope you learned something meaningful today. If you enjoyed playing detective with data, don't forget to like, share, and subscribe to AlgoStalk. There's a new mystery around the corner, and I'll be right here to solve it with you. Until next time, keep learning, keep stalking the algorithms.